Hello everyone. How is everyone doing? There's no one here, so I'm just asking for to myself, I guess. Well, what we're gonna do today, we're gonna do something a little bit different. The last time we did banded, we solved the over the wire banded from 1 to 20. Took like 2 hours, but anyways, we kind of learned some new things. And this time we're gonna follow another fellow hiker. I don't know him personally, but he has a great page about malware development. It's Cocomelon Chief. And we're gonna follow his tutorials. Tutorials, not exactly tutorials, but they kind of explain his journey in learning malware. So let's start with the first one. Welcome to my cybersecurity path. Welcome, yeah. He will describe techniques for the successful for red team. Great. He will be running black box pen testing, meaning that the hacker has zero knowledge about the system. Gray box, the attacker has a little bit of knowledge, and white box, the attacker has full knowledge about this the OS, the company, or whatever he is attacking. Black box, he knows nothing. He has to learn everything. Lateral movement, meaning after the initial access, where you go and hack into a computer to physically be able to execute commands, you will do some commands yourself to maybe have a backdoor, which will allow you to to connect back again. Automation on written scripts essentially it will help us do some things not manually because if we do it manually it would take a lot of time. So automating it just save us a lot of time. And development and analysis of malware. Those are two separate things. Malware development and malware analysis. Analysis is done by the blue team, which essentially are trying to understand what the malware does and how it is done. They may not be able to see directly the code, but they will probably be able to see the assembly of the code. Maybe even use a disassembler like Ghidra to reverse engineer it, or like an online one like Godbolt. No, Dogbolt, Godbolt. Which one is it? Godbolt. No, this is the compiler. Dogbolt is the decompiler, where you can just drop a file inside and it will tell you the code. I think this is like you put in the assembly and it decompile it, and the Godbolt does the opposite. You give it the code and it gives you like the assembly. You can do not assembly. Let's do C. Yeah, okay. This is an example where this is the assembly code with GC compiler. We can also do minus O3, which will give us how the computer might make it faster. What's the term? Improve its performance. Um, okay, so let's continue. Most of the tutorials require a deep understanding of the Python and C++ programming languages. Okay, I don't have a very deep understanding. I do understand and I can write a code, but I would say I'm more of an intermediate and I have never written C++, but I have done C and it's close. It's not the same thing because it essentially adds functionality in the C++ to the C. So I can do like C stuff in the C++, and because I have done also Java, I can also do the op O OOP operation object. What's the OOP languages? What's object-oriented programming? Yeah. So essentially like things like inheritance can be done and etc. Okay. There's a GitHub repo of him which provides the code, most of the code. Okay, so let's start with the antivirus engines evasion for C++ simple malware. Hello, cybersecurity enthusiasts and white hikers. Great. Okay, in here we can see a Python program and also a C++ program. It might analyze it later, so we will skip it for now. Um, this is not a tutorial to make malware, understandable, but a practical case for educational purpose only. Amazing. AV evasion has always been challenging for red teamers and pen testers, especially those who write malware. Agreed. Um, in our tutorial, we will write a simple malware in C++ that will launch our payload calc.exe. Okay, calc.exe is a file in Windows where it's essentially the calculator, the calculate process. If you go into a Windows machine and type calc.exe, you will essentially see a calculator. It will probably show us later. Then we check through virus total how many antivirus engines detect our malware. Virus total or hybrid analysis, that's that one as well, will take your sample like the calc.exe and analyze if it is malware or not. If it hits some flags like there is no certification, it will raise a suspicion that it's actually malware, not a legit program. I will detect our malware, after which we will try to reduce the number of antiviruses. Okay, great. Let's start with the program. Okay, this in here he includes some libraries, Windows.8, SDDO, stdlib, and strings. Okay, Windows is for the Windows API, if I'm not wrong. SDDO is for input and output. stdlib is the library, and string H is for strings. Here is the payload. So when someone actually executes this, he will get the calc.exe. I think he will show it. He will probably show it. No, he does not show it. Okay. Then he initializes the length of the payload using the function sizeOf. SizeOf returns the actual length. For example, this counts as one, so it's 1, 2, 3, etc. Then he initializes the main. The main function is the function that will start when you execute the program. Anything outside of it, it will not execute until it is actually told by the main. So now he initializes the payload memory. So he will probably allocate some memory like in the heap. Initialize an RV as a boolean. Boolean is true or false. H handle th. I'm not sure what handle does. Let me check. Handle, let's see, plus plus. Handle is an opaque. What is opaque? Opaque type. Opaque type. No. Uh, a user a user defined or built-in data type that is fully encapsulated. Okay. Data type whose concrete data structure is not defined. Okay. User friendly. Okay. I still don't fully understand it. Rust compile development. Opaque types are syntax to declare an opaque type alias. What? Let's see an example. What is an? Oh, this is an opaque one. Okay, I understand this. This is like closed within the what are those called again? I don't remember. Not parentheses. Parentheses are this. This is don't not fully sure. Let me check it. what is it? It is a curly break brackets. Curly brackets, yeah. I totally forgot it, but that's totally fine. Um, okay, great. Give me one sec. Okay, that's great. Cool. So it will handle it handles an opaque type. In all ways, it used to get reference to an object. Okay, basically it's just a key on always used to identify all objects contained in it. Every handle contains a numeric value which is stored in a large table that the OS uses. Okay, allows to manage errors. Exception handle, no, not exception handle. Handle command a pointer to an object located. Okay, so this essentially points, it will point somewhere. And D word, a double word, meaning 4 bytes, if I'm not wrong. D word, bytes. I think it's four. Four, yeah. A word is 2 bytes. A D word is four, and a Q word is eight because it's quadruple. Quad word, yeah. In here it allocates the memory can, yeah, okay. So in here he will allocate memory to the buffer, essentially inside the heap. My payload mem virtual alloc is a function building the Windows.h library. Microsoft actually has a really great page where they explain everything, so we will actually just search for it. Virtual alloc reserves, commit, or change the state of origin of pages in a virtual address. Okay, for those who don't know what's a virtual address versus physical. Oh, yeah, okay. This is the virtual address, and this is the physical address. Pages are those in between. I think they're also called frames, if I'm not wrong, but they usually call them pages. Um, so essentially, this can reserve one, change it, or what? Or commit. Okay, so commit will make not a new one because we cannot physically make new spaces. Um, the state of origin, okay, of the calling process, okay. Memory allocated by the function is automatically initialized to zero. Okay, so tells us that when we initialize it, everything inside the virtual memory is gonna be zero. To allocate memory in the address and not space, we use virtual loc x. So this is another function as well. Its syntax is this. So it is optional that you will use an LP address. You will definitely need the size, the allocation type, and a FL protect. I'm not sure what this FL protect is. Let me see. The type of memory allocation. This part number must contain of the following values. Memcommit. I think we see memcommit here. Yeah, so we see, firstly, let's close this. Okay, so firstly, the LP address, it is initialized as 0. Then my payload length is actually the size. FL allocation type is gonna be mem commit and mem reserve. So what are those? Mem commit allocates memory changes for the overall size of memory and the paging file on the disk, or the specified reserved memory pages. The function also guarantees that there is a call rate to initialize the memory. Okay, so this actually just allocates memory. It will do the change. It will change the memory address. So if it is 0, it will go to like an address like 0x1111 example. And the reserve is gonna arrange a person without allocating any actual physical storage. Reserves arrange. Okay, so those that reserves some virtual address space without any allocating any physical space. Okay, so as we saw before, virtual address. It essentially tells us that it will allocate some addresses here, but there will be no connection to the physical address. if I understand correctly. Then there is the page read or write, and it will essentially be able to read or write with the allocation. Let's see if I'm correct. Where is it? Large physical. Okay, no, this is default protect. So right now we're in the protect. Return. No. Where is it? Default protect is gonna be a D word. No access, guard, memory. Okay, let's say those. Memory protection constraints. All of the memory you must specify another volume. Okay. Okay, so in here we can see the constraints. We see that it always needs to be a page and then a word like execute read, etc. I think if you do actually do if you actually use the execute, it will raise some flags if I'm not wrong. So they usually avoid it in the beginning at least. And she will load page read and write, which will return 0x4, which is actually 4. This is in hexadecimal. Copy payload to the buffer. So this just allocates it, and this copies the actual payload to the buffer that we just allocated above. So RTL move memory. Let's close this. Let's search for this. RTL move memory copies the content of our source memory block to a destination memory block and supports overlapping source and destination memory blocks. Okay, so this copies the content of a memory block. So in our case, this is the memory block. So in the first one, we use the destination, then the source, and then the length. So we wanted to go to the payload memory, which we initialized here as a pointer. The source is my payload, which is this, and the length, which is like the last. The length of the actual payloads where we initialized right here. Make new buffer as executable. Okay, so virtual protect. What does virtual protect do? Let's find out. Although I have seen them sometimes, I don't actually remember them because I have not seen them enough times. Sends the protection of a region of committed pages in a virtual address of the calling spaces. Okay, so this just changes the protection. The new protection and the old protection. So what protection it used to have in the as the last parameter, and what new protection we wanted as the new protection. I don't know if I just did it right, but so virtual alloc the yeah. So essentially he changed it for from the all protect. The all protect is initialized. Where exactly? All protect is initialized as 0. So this just gives us the address of this that points to this 0. And we change it to execute and read. Execute and read as we saw before. I think it's gonna be in the constraints. And where is it? Virtual log memory. Yeah, it's in the again inside here. It's the execute read. Execute read. So execute read, enable execute, or read only access to the committed region of pages. So we can actually only read and execute, but not write. You have 2 out of the 3 um, permissions. Okay, yeah. And we check if it's different from 0. When is it 0? We need to check. Let's check virtual protect. It's essentially a bool. So I think false is for false in a decimal. I think false is 0. Yeah. If it's 0, it's false, and if it's 1, it's true. Um, oh God, I forget all this. Okay, if the function succeed, the return value is non-zero. Okay, that's all we need to know. So if this is successful and we do actually make it executable, then we can run the payload. If not, we cannot, and we just return zero to the program and it stops. So if this actually passes through, we can run the payload, which creates a thread. A thread actually will execute, I think, our code that we allocated, not the code it will execute well with. Create a thread to execute within the virtual address space. Okay, so this just takes it and executes it, but this is only true because we actually did change it here to be able to be executable instead of only read and write. So this is create a thread, it gets 0 and 0. So this is the thread attributes. This is optional. The stack size, the initial size of the stack in bytes. Okay, so this is 0 again. LP thread start routine, my payload mem. Yeah, this is the start address. So what does that do? No idea. Let's search for it though. The function pointer. So this is a pointer. Points to a function. Okay, so that points to a function. This this is not a function. This is actually a pointer which points to the memory, which points to this, which is a function. Okay, so this essentially points to the memory we allocated, and it starts here. And there are three zeros. It is the LP parameter, the dword creation flag, and the ID. If it's 0, runs immediately after creation. If it's 4, the thread is created and suspended and does not run until resume thread function. Okay, we don't have a resume thread. Okay, and then wait for single object. So this will wait for it. Wait for I think it will wait until there is the CPU can execute it. Wait until the specific just signal state or the timeout interval elapses. So this just waits until the thread can be executed, and it gives it the thread that we created and a -1 what for in the milliseconds. -1 y -1 not zero is net the function when the up signal. Okay, okay, we have a negative, so I'll wait until the optic signal or the interval elapses. Okay, I don't know. Okay, so this is irrelevant. Okay, so we just have one function. Okay, he explains it. I just did explain it on my own, but let's hear it from the creator himself. So we have just one function, okay, int main void, and we have the size of payload. Where is it? Size of my payload is actually here above, which is not shown here, but sure. For simplicity, we will use calc.x. Okay, he tells it calc.x as the payload. So this payload just opens the calculator in the Windows machine. Without delving into the generation of a payload, we will simply substitute the finished payload in our code. Great. And the main logic in our main function is this. I explained it, but we will see it again. Let's go investigate this logic. If you want to run our payload in the memory of the process, we have to do a couple of things. We have to create a new memory buffer. Okay, the memory buffer is created here with virtual log. Copy our payload with the RTL move memory and the buffer and start executing the buffer. This will execute it. The wait for single object will execute the thread. First, we do have to allocate the new memory. Okay, this is simple enough since without the actual memory we will not be able because the CPU fetches memory from the RAM and it executes it. That's the logic it works. The first it uses the von Neumann architecture. So the first we do the first we do the first we allocate new memory region in a process and we store an address in my payload memory variable. Okay, and this memory region is readable and writable. We can see it right here that it's readable and writable, and the store is the commit, the reserve. It commits, and the reserve is to reserve it, to store it. And this memory is read, okay. Then we copy our payload into the memcop, copy the actual payload in the memory and the length of it. Then we set our buffer to be executable. We do it with the virtual protect. It changes from the all protect to the execute read. Okay, everything is good, but what am I doing in this 44? Okay, so yeah, as I said before, why do it here, not here? Why not allocate a buffer which is readable, write, and executable? The reason is simple, as said, some hacking tools and antivirus engines can spot this memory region because it's quite unusable. And the process needs a memory with its readable, writable, and executable at the same time. So to bypass this, okay, some hacking tools. Oh, okay. He just says that if you have all the three permission, it's super unuseful and it needs to be super specific to have all of those permissions. So it just raises suspicions. It is better because you can do everything that you want, but it's easier to find from the antivirus. To bypass this, we do it in two steps. And if everything goes well, we run our payload as the separate new thread in the process. Great. Okay. Let's see if let's see if I can do something. Podium, a new file. Let's example.c++ because it's C++, and we can copy the code. Okay, what? Let's ignore that. Let's go here, open this, close this, and paste it here so we can see it. Great. Okay. I could do it before, but that doesn't matter now, I guess. And if everything okay, the new thread in the process. Okay, yeah. Um, let's go. He then compiles it. I think I can compile it. Let's save it first. GCC, the example. Does he use anything else? Okay, he uses quite a bit. He uses -o, which says it in a new file called eval.exe, -s, -f, function section. I don't know what those do, the rest of them. -w no write strings. It doesn't know how to write strings. -f no except exceptions. It does not. We do not want to show any exceptions. -f merge -all constraints constants no constants static -lib std c++ static -lib ccc. Did you mean okay? Let's see where are my mistakes. Function check. It's sections, not section. Sections. Sections where have no exceptions. It is exception. Oh, it is exceptions. F O. I said, oh no. Okay, Windows 8. Okay, it does not know that. GCC, I think. What? No input value. GCC example. It does not understand what it's. Okay, let's leave it for now. Since I'm in the Ubuntu machine, he's in a calm machine, so it works. But okay, let's forget about it. And administration. Okay, you can see it right here. So basically, this is how you can store your payload in a .txt section. So we do not have an executable, but we will have it. Let's go to my downloads. Is there? Okay, this is an executable. So let's do object dump minus v and bin .exe. Uh, okay. Uh, do we see that? No. Okay. There are the sections. Where is it? Okay, yeah. So there in every .exe file there is the .txt section. And here he did it. Where did he do it? Okay, he just explains that you store your file in the .txt section without encryption. Encryption actually helps it uh, from malware. If I'm not from malware, it helps evade it. Impersonate it is not malware. Let's go to upload a review. Okay. So he actually uploads it on virus total, and it tells us that there are a lot of flags. So there is a high chance that this is a malware. 22 of 16. Okay, let's go try to reduce. Okay, so now he will show us some techniques to actually reduce the number of detections. For this first, we must encrypt. We must encrypt. Where was I? For the first, okay, we must encrypt our payload. Where we want to encrypt our payload, the basic purpose of doing this is to hide the payload from someone like antivirus engine or reverse engineer. The purpose of encryption is to transfer data in order to keep it secret from others. Okay, so we don't want anyone to know. For simplicity, we'll use XOR encryption. Okay, XOR encryption is actually pretty simple. Let me show you. So XOR actually is when you get two gates. If it is, you get two inputs. If both of them are 0, 0 closed, you get 0. If either one of them is open, you get 1. But if both of them are open, you get again 0. This is actually a simple way. So you get like plain text as a random secret key, which will be a combination of 0 and 1. And if it is 1, 1, you get 0. If it is 0, 1, 1, you get 1. 0, 0, you get 0. Simple. This is the XOR encryption. Close those. The purpose of the encryption is to transform data in order to keep it secret from others. For simplicity, we will use XOR encryption for our case. Let's take a look at how to use XOR to encrypt and decrypt our payload. Okay, let's see the updated one. We can copy it, but we'll do it manual. Okay, so Let's go here. Let's put it on the right side and let's put this on the left side. Okay, so what he does is this is the payload. Come on. Yeah, okay. So this is the payload which has the length, and right here he chars his secret key in a list. Gives it up my super secret key, and this will essentially this is my secret key is gonna be uh, the the bits for that the extension will happen. So this essentially just takes its key, its character, it breaks it up into bits, and it uses those bits to encrypt the payload. Um, let's void a function. We give it data size t data length. This is the length char of the key, the pointer to the key, size t, the length of the key. So this is the data that we want to encrypt, and its length, and the key, and the length of the key. We initialize j. And then we do a loop. We'll do a for loop. If you are familiar with for loops, essentially it will repeat a number of times. We give it that amount of times. It's gonna be the data length. If it's like 5, it's gonna do it 5 times. If it is 15, it's gonna do 15 times. We initialize the I, do it while I is less than data length. If it's equal, it just stops. And we check if the j is equal to the key length minus 1, j is equal to 0. Okay, so we will check its time if the length of the key is essentially greater than 0. Key length is, yeah, we get from here if it's 5. We check if j is greater than 4, and then we add to the j1, we change data I into data I to the power, now to the power of key, and j. Okay, and we increment the j. So let's check if it is like if j is equals to key length, and if this is true, it gives j0. And the data actually changes from data I think we can, this is the exact same thing, power equal if I'm not wrong, this is the exact same thing. I just told it to let it be known, and it essentially puts inside each character of the data, like it goes here. It XORs it with this, with the j, with the j key, with the j character of the key. Essentially, it's going to do it for first for the m, then the y, then the s, then the u, then the p, etc., and for each one of them. This is going to be done extremely fast because this is it's going to be faster if it was assembly. And what else? What else? Let's see. Let's see. In main void, it's the exact same thing here. Payload, okay, and then we XOR the payload. We do it after the allocation because it doesn't matter before the allocation. It matters because we want to change it here. So we call the function XOR, we give the values. First, we give that it's a pointer to my memory, my payload memory, which is also a pointer. So this will point to this. Then we give the length. So it's gonna be the length. Note this, the length. Then we do the secret key and the length of the secret key. So this is the secret key and size of my secret key. And we put the question mark at the end. And that's all. Okay. So we just initialize our key, the function, and we call it before the payload is copied to the buffer. The main difference with our first simple implementation is we add XOR decrypt function on our secret key to my secret key. Yeah, this just tells us how to XOR it, how to decrypt it. He does he do it in a different? No, okay. So this instead of is there a difference actually? No, this is just this is the decrypt, right? Where's the encrypt? Decrypt. Okay, so there is not. This is gonna be just the same thing. Decrypt you and you decrypt again. XOR, decrypt the XOR. Oh, okay. So what he does is not actually XOR it. He actually just de-XORs the payload here. So the payload is actually right now XORed, and we just reverse it. We decrypt the XOR that was done. Okay, it's actually a simple function. It's a symmetric encryption. Okay, there's two types, symmetric and asymmetric encryption. If I'm not wrong, the symmetric has the exact same key, as the public and private key, and the asymmetric encryption has different key, private and public keys. Let's see if I'm correct. Symmetric versus asymmetric encryption. A single secret key to encrypt the decrypted data, while asymmetric use a pair of keys, a public and private key. I was correct. And the only missing thing is our payload. Yeah, so that's the reason he didn't have a payload, because it was XORed. Here certainly we have an XORed payload, which should we encrypt with XOR. Yeah, this function actually just XORs it. We will XOR it in a different file, and this will read that file and XOR it. For that, we will create a simple Python script. He will import C, so West has lib and strings, XOR it with a similar way. Key is gonna be the string of the key. The key is gonna be initialized here, my secret key. This is the encryption, and this is XOR function to encrypt the data. What's the difference between those two? XOR function to encrypt data, encrypting. Okay. So open and replace our payload in C++. Temporary open, evil XOR C++. It will just replace the evil C++ with its evil XOR, which will just add the payload XORed. Data temp read, you will read the file. It will replace the payload with the ciphertext that we will XOR. It will close it. It will open the encrypted C++, and with write. This is read. This is, I think, read text. Write. I don't know what the write class is. Python open. What is plus? This is right. Where is plus? Where does Stack Overflow say? If it ever opens. The opening exactly okay. Opens for reading and writing. Open this file is created. File is created. Okay. Okay, so this just gives reading and writing. So why not do RW? I don't know. Not gonna question him. And he will write in this program and will close it, and then it will try to compile it using the GCC compiler. It will catch an exception, and else if nothing happens or if there is not nothing, it will just print the CMD and successfully compile. Let's see the above code. The XOR, he gets a data and a key. The key is gonna be the string key. L is gonna be the length of the key, and the output is gonna be for now nothing's gonna be empty. It will repeat for the length of the data, like from 0 to 1, 2, 3, 4, 5 until the length of the data. Current is equal to data I. Current key is key. It's gonna be data. Let's see what we call it. XOR. This is the XOR plane. Often, where is it? Where does he use it to show it as an example? He used it here. Okay. So he will just get the data. It's data. It will. This is a mod. And the key is gonna do the. What's gonna do? It's gonna take the range, like it's 1, 2, 3. This is gonna take like that number and mod it compared to the length of the key. Or it's gonna be a lambda. This is lambda function, which essentially just do a function inside here. So it's gonna do x for x if instance xy. So this is gonna give us f if x is instance. What is instance? Python. If instance returns true if the specified object is on of the specified types. Okay, so this will check if it is int, if it is an integer. Else it's gonna do ord x. Ord x, I think it's gonna do a byte. Byte, is it byte? Return the integer. Okay. Oh, okay. So this is representation of it in ASCII. This is gonna do 104. Let's search ASCII table. It's gonna be 104 if I'm not wrong. Let's search for a bigger image. 104. Yeah, it's gonna be 8. I don't know if you can see it, but you just have to trust me on that. 104 is the 8. So this just explain if it's int, it's gonna keep it an int, and if it's like a character like age, ABC, it's just gonna give us a number corresponding to that in ASCII. And the output is gonna be output plus the character or it's gonna be this function to the power. This is like the exoration, I can call it, maybe, meaning that he XORs the current and the current key and just adds it to the output str. The output is gonna start with nothing, and then on the first time it's gonna add the first one, then on the second one it's gonna add to the first one, the second one, etc. And the XOR encryption actually gives the data on the key to the XOR, The ciphertext is gonna be 0x plus 0x. Why is that? I don't know. And it will join hex in hex. No, okay, it's in hexadecimal. It's gonna join every two, or for starting from two, it will start from the second character. Maybe the first two is gonna be zero. For x for each character in the ciphertext, and it's gonna do OR x, which is the same as here. So the character corresponding to the number, and it's gonna hex it. Hex Python, I think it will. Yeah, it will change it from a decimal to a hexadecimal. So 255 is gonna be 0xff. So that's why he just said it 0x. So this is gonna be 0x, and it will start from the second, probably. It will print it and it will return the ciphertext and the key. The key is just gonna be the key that we specified. The payload is gonna be calculate.bin with read and this is read bytes, and it will read it. The ciphertext is gonna just encrypt the plain text. The plain text are those, the payload. The secret key is this key. Essentially, the payload is gonna be inside the calc bin, which will be read, XORed, and then thrown into the ciphertext and the key. And it will change the payload. The payload in this program, the example.c++, which he calls evil encrypt, and he will compile it. For simplicity, we will call it Caliban payload, this payload. But in real scenarios, you can use something like MSF Venom. MSF Venom is a Metasploit framework which will automate that for you. It will automatically generate a payload, and for that instance in x64 and the reverse shell. The reverse shell actually allows a hacker to execute code from another computer and force that connection, if I'm not wrong, and name it hackbin instead of like calcbin. Then he run it. This will encrypt it for me automatically. This he just like does an automation instead of doing it manually, and it will create the evil encrypt, not the evil XOR and the evil encrypt C++. And we can write in the victim machine a Windows 10 in this case. Most machines nowadays do have the architecture of x64, so you can just run the x64, but x32 works also. Um, we can also see that the flags went from 20 to 18, so 4 flags just disappeared, so that's good. And gives this link, and so we have reduced, yeah, okay. And this is the source code for virtual log, the move, object, and everything he does. Okay, so that's everything for today. We will continue to another day with the next lesson, which is gonna be the part 2. And that's everything. Thank you all so much for watching. I really appreciate everything you've done for me, and see you in the next one. Bye bye.